Great. Thank you all for coming, and thanks for allowing me to do this virtually. I'm actually in Berkeley for the semester, so getting to Montreal would have been a little more difficult than coming from Atlanta. Yeah, so if at any point you have questions, I might not be watching the chat, so you should feel free to just interrupt. Okay, great. So today I'm going to be telling y'all about smooth knot concordance and homology cobordism. And I'm going to start with a motivating conjecture. And this is a conjecture due to Kirby and Akbulut. It's in the Kirby problem list. And it's from about the mid-70s. And it goes as follows. If I have two knots, K1 and K2, and they have homeomorphic zero surgeries, the conjecture stands that this would imply that the knots are smoothly concordant. And I'm going to provide some background of this question and what's already known, but first maybe I'll give a couple of definitions. And if at any point I don't provide a definition that maybe you need, you should also feel free to ask for it. So what is a zero surgery? A zero surgery is given some knot K and S3. I remove a neighborhood of the knot, and I glue in a solid torus, and S1 cross D2 in such a way that the meridian of S1 cross D2 goes to the zero framed longitude of K. And we refer to this three manifold that we get as a result using the following notation. And this denotes the zero frame Dane surgery of a knot K and S3. And maybe I'll also remind us what smooth concordance is. So we say that two knots K1 and K2 are smoothly concordant if they co-bound a smoothly embedded annulus and the product manifold S3 cross the interval. And then we can build a abelian group, which will denote C sub smooth as the smooth concordance group, the concordance group in the smooth category. If we take isotopy classes of knots with binary operation connect sum, and we mod out by this relationship, which is an equivalence relationship. And then identity elements in this group are the knots that are smoothly concordant to the unknot, and we'll refer to these as slice knots. And maybe if we're being careful about categories, these are smoothly sliced knots. And we can equivalently think about these as knots that bound a smoothly embedded disk in the four-ball. Okay, so this conjecture is saying if there's this sort of, if these three manifolds that we can correspond to the knots are the same, then somehow there has to be some sort of sameness between the knots themselves. And so now I'll provide you with a little bit of history of this conjecture and what's been shown already. So maybe we'll just say history. So very first, in 1978, this is due to Kirby and I believe Melvin. And they showed that this is always true whenever one of the knots is the unknot. So whenever the unknot shares a zero surgery with some other knot, then that knot must be smoothly sliced, particular. Okay, and then in 1983, Livingston gave a counterexample more broadly via a family of knots where K was not smoothly concordant to its reverse, which is if we take the knot K and just give it a reverse orientation. So in particular, as the construction of a zero surgery is independent of orientation, of course, a knot in its reverse will have the same zero surgery, but in this case, these knots were not smoothly concordant. So then it was popular to think about this sort of abridged conjecture. So now maybe we'll ask an AK prime, meaning just the ocvolute curvy conjecture with a little bit of an adjustment. We say, okay, well, what about if the zero surgeries on two knots give the same manifold? Does this then imply that the knots with relevant orientations are concordant? Okay. And then it wasn't until 2011, and this is a result of Cochrane, Franklin, Hedden, and Horn, who showed the following. Suppose instead of being homeomorphic, our zero surgeries share the following relationship, that they are homology cobordant relative to meridian. And I'll give you that definition in a moment, but they showed that this relationship is not strong enough to imply that the knots be smoothly concordant. And so what is this relationship? So first, just an integer homology cobordism between 2,3 manifolds is a 4-manifold W, such that it is its boundary is these 2,3 manifolds, maybe one with reverse orientation, in such a way that the inclusion maps on the boundary induce isomorphisms on homology. So that's just in general homology cobordism. And since we're saying integer, that just means with integer coefficients. And then this additional requirement, this relative to meridian, is a meridian conserving condition. And what it just means is that the positively oriented knot meridians of my two knots are homologous. So as representatives of homology classes in H1, they represent the same class. So this helps us to deal with orientation a little bit. It fixes that orientation. So, right, so the statement says that this is not strong enough to imply that the knots are smoothly concordant. And then finally, most recently, in 2015, Yasui just gave like completely disproved this ocvolute curvy prime via a family of counterexamples. That we'll maybe just note are strictly non-slice. Okay, so I've given you a conjecture and then I've told you that it's not true. So what kind of remains open? So yeah, what is open? And we'll make maybe a few remarks about, in general, why this family of questions is interesting. So I claim the following. This is sort of a well-known result, that if we assume, this is a large assumption to make, but if we assume that the 4-dimensional smooth Poincare conjecture is true, then what this would imply is that if we ever had that the zero surgeries of two knots are homeomorphic when one of the knots is slice, then the other knot would have to be slice. And so what this tells us is that in general, if we are trying to maybe find some counterexample, and we're looking for an interesting way to build exotica, that this is like a good place to look. So to try to build out examples where we have potentially that some knot is sliced and shares a zero surgery with a non-sliced knot. But this is obviously a very difficult question to answer. So what we will ask instead is a slightly weaker condition. So I'm going to ask the following. So maybe we'll say this is our question today. If I have two knots whose zero surgeries are homology coordinate relative to meridians, they're not quite homeomorphic, but maybe not, so far away. And I further require that one of my knots be torsion in the smooth concordance group. And we'll note that if anyone's unfamiliar, the only torsion in the smooth concordance group that's non-trivial is order 2. Everything else is either slice or infinite order as far as we know. And then I further require also that my knots be smooth, be sliced in a different category. So I'm going to say that they are, this is maybe R, rationally sliced. And I'll define that for you also. So this is a slightly weaker condition, well, definitively weaker condition than smooth sliceness. And what it means is that instead of necessarily bounding a smoothly embedded disk in B4, we just require that they bound a smoothly embedded disk in some rational homology 4-ball, meaning some 4-manifold that has the same rational homology groups as B4. So not quite smoothly sliced, although we'll note that, of course, smoothly sliced knots are a proper subgroup of rationally sliced, sort of a generalization. So we're going to ask if I have all of these requirements on my knots, maybe I'm trying to approximate smooth sliceness without actually achieving it. Is this enough to require that my knots be smoothly concordant? And my answer is no. And maybe we'll write as maybe a theorem that there exists a pair of knots, K1 and K2, such that their zero surgeries satisfy this equivalence. They are both rationally sliced. K1 is order 2. And maybe I'll say it as it's a representative of a 2 torsion class. And K2 is infinite order. So what I'm going to show you today is sort of the proof construction for how this result goes, and also in particular, sort of going to give you a little bit of an example of how this is sort of maybe a new-ish technique for how to obstruct a knot from being finite order in the smooth concordance group. So has the potential maybe to be used in broader context to continue to ask questions like this. So yes, so now I'm going to introduce our knots. Maybe I want pictures for this. I have pictures here. Okay, great. So what are the knots? So our knots are going to require us to recall the satellite construction, which is I've given a drawing of here. So given some knot, we'll call it P, and it's sitting in the solid torus, we'll map it to the tubular neighborhood of a knot K. And we'll map it in such a way that the longitude may be described by S1 cross a point where the point is in the boundary of D2, gets sent to the Seifert longitude of K, which again is the 0 framed longitude. So we think of this as the longitude with linking number 0 with our knot. And then when we do this, what we care about is the image of P under this map, and maybe we'll rewrite it as PK. And this is the satellite knot with companion K and pattern P. And if I've drawn it correctly, it will be right there. We are. This is sort of an easy example to draw because the figure 8 knot, which is this that I've drawn the tubular neighborhood of in green, has Reith 0, so we don't have to care about any framing issues. The framing matches up. And I've chosen this example because these are exactly the 2 knots that we're going to use. So maybe I will draw them again down here. So I won't draw the satellite knot again, though you'll just have to keep that in mind. But our knots are the figure 8 knot and the satellite knot that we get when we take the major pattern of the figure 8. And I'll explain why I've chosen those knots now. So 4-1 is the figure 8 knot. That's just the Alexander-Briggs notation for it. And this is the figure 8 knot. Okay, maybe reorient it. And the reason this knot was chosen is, well, it's torsion, and the way to see that is that it's negatively amphichiral, which just means that it is this knot is isotopic to the knot that you'd get when you take its mirror image. So you swap all of its crossings and you take the reverse orientation. Maybe I'll write that. So swap its crossings and take reverse orientation, and you get a knot that's isotopic and it's not smoothly sliced. And these two conditions together tell us that this knot is ordered 2. And then we also know that it is rationally sliced, and this is due to work of Tim Cochrane based on earlier work of Fintuschel and Stern. So we have that this knot satisfies the conditions I outlined earlier. And why are we taking this specific satellite? So we'll denote as Q, this is the major pattern. It is famous in 4-dimensional topology for reasons related to building exotica. But the reason we like it maybe is it is an unknotted pattern with winding number 1. So what does unknotted mean? This might not be a standard phrase, but what I mean when I say that a pattern is unknotted is that if I take the image of the unknot under this pattern, it gives me something that is unknotted in S3. And then what that would imply for us is the following. I'm going to give a schematic here. So recall that what I've just told you about this knot being rationally sliced. We can think of that schematically as there being a concordance between, a rational concordance between the unknot and our knot here, the figure 8. And then the point is that, and this is maybe a little not so rigorous, but just a picture to keep in mind, that when we take the satellite, we can sort of think of taking the satellite on both ends in sort of a non-rigorous description. And what we'll get is that in particular, this concordance in this category holds. So since the image of the unknot under Q is just the unknot again, well, then the image of our knot under Q will then also be rationally sliced. So this tells us then that Q of 4,1 is Q slice. And this is a condition particular to unknotted patterns. And this is true for any category of concordance or sliceness. It's preserved undertaking this type of pattern. And then the reason that we care about this sort of larger classification of this pattern, that it's unknotted with winding number 1, is the following. There is a result of Cochrane, Franklin, Hedden, and Horn in the same paper as mentioned earlier, that for any such pattern, so unknotted with winding number 1, for any knot, we have the following, that their zero surgeries are of the satellite, and the knot will always be homology coordinate relative to meridians. So maybe to summarize what we have, or what I maybe hopefully convinced you of, the figure 8 knot has a zero surgery that is homology coordinate relative to meridian of its satellite under the major pattern. 4,1 is torsion. And these two knots are both rationally sliced. And so the question that remains, too many cues. The question that remains is, are these knots smoothly concordant? And as we've claimed above, the answer is no. And furthermore, we claim that this knot represents an infinite order concordance class. Okay. So I will now show you that that is true. And maybe we'll sort of claim that this proof technique seems like sort of using a sledgehammer to hammer in a nail, but we'll see why this knot in particular is a little bit difficult to answer. Like, it's a little bit difficult to understand the concordance order of this knot for reasons that will become clear as we go. So in order to answer this question, I have to introduce a lot of Haggard-Floer theory. And yeah, I just want to repeat that, like, if there's any questions you have along the way, you should maybe ask them. I'm trying to maybe assume that there isn't a lot of Haggard-Floer experience in the audience. So if I miss anything, you should maybe just ask. But we'll start with knot Floer homology. And this is a theory due to Oshvath and Sabo, and independently to Jake Rasmussen. And the theory associates to some knot K and S3 a bigraded chain complex. And this chain complex is freely and finitely generated over, we'll think about it as over the ring, the polynomial ring with two variables, with the field coefficients in the field of two elements. And there's several sort of famously interesting properties of this theory, in particular that it categorifies the Alexander polynomial, and it detects many interesting topological properties of knots, including genus and fiberedness. But maybe we'll point out a limitation of the theory for what we would like to ask. It's the following. And this is sort of, this limitation is a motivation for a lot of recent refinements of this theory, but that there's not a well-defined way to go from the knot Floer complex, which we denote CFK sub R, of a knot to the knot Floer complex of a satellite. And this would somehow be, a very helpful thing to be able to do, in particular, because, for example, for us, we very well understand the knot Floer complex of the figure 8 knot. It's quite a simple knot. The knot Floer complex has been understood for quite some time, but there's no well-defined way to sort of transform the knot Floer complex of a knot to the knot Floer complex of some satellite. However, what we can do is use a refinement of this theory in the form of ordered Floer homology, which I'll talk about in a moment. So that's what we'll use to address that issue. And then maybe to motivate why I'm even looking at knot Floer homology at all to answer this question, we'll maybe recall that there are several concordance invariants. Sort of living in the knot Floer framework. So they're invariants that we can compute given the knot Floer complex or the knot Floer homology of a knot. Maybe I'll just give a few examples so maybe you can have an idea of what they look like. So maybe due to Oshvath and Sabo, there's the tau invariant, which takes on integer values. There is, due to Hom, there's the epsilon invariant, which takes on values -1, 0, or 1. And maybe due to Oshvath, Stipschitz, and Sabo, there's upsilon, which assigns a piecewise linear function on the interval 0 to 2. And so in particular, these invariants are helpful for obstructing smooth sliceness. If we get any non-zero answers for any of these, we can conclude that our knot is not smoothly sliced. But a limitation again of this is the following, that these are in fact rational concordance invariants. And so they cannot detect the subgroup of non-smoothly sliced knots within the group of rationally sliced. And that's exactly what we would like to be able to detect. So somehow all of these concordance invariants vanish for our knot, and so do other invariants, the S invariant coming from Kavanagh homology, and even there are several smooth concordance invariants that also vanish. So basically everything vanishes for the knots that we have because they're rationally sliced. And so what we will use to address this limitation is another refinement. And so we will use involutive knot Floer homology to say something about concordance. So we will use bordered Floer homology to build the knot Floer complex of the knot that we require, and then we'll use involutive knot Floer homology to make an argument about its concordance. Great. So before I maybe dive into the bordered Floer theory, are there any questions at this time? Okay, great. So bordered Floer homology is a theory due to Lipschitz, Oshvath, and Thurston. And it is a Haggard-Floer theory for 3 manifolds with boundary. And we'll maybe restrict to thinking about 3 manifolds that arise as link or not complements. So in particular, we'll restrict to thinking about torus boundaries. This is sort of the simplest version of this theory and all we need for what we're trying to do. And so the way the theory works is thus: we have some 3 manifold, which maybe we'll just say has a single toroidal boundary component. And what we do is we assign to the boundary, or maybe associate to the boundary, differential graded algebra. And actually, in the case when my boundary is torus, this is called the torus algebra, fittingly. And it's actually just a graded algebra. And then our invariant in this case is the homotopy equivalence class. Of either of two differential graded modules over this algebra. And so sort of the point here is that this invariant seems to come in two forms, but it's actually an equivalent invariant. We can choose to view either CFA hat, which is referred to as the type A structure, or CFD hat, which is the type D structure. And maybe this is a notion of equivalence, and it's more of actually a duality. And so what's going on here is that these invariants capture precisely the same data about our three manifolds. We don't necessarily gain anything by looking at one of the structures or the other, but sort of the purpose of having this dual is the following. Lipschitz, Oshvath, and Thurston introduced this pairing theorem, which is really the beauty of this theory. So given two three manifolds, M1 and M2, with boundary, it'll just say boundary the same genus. And some map H from the boundary of M1 to the boundary of M2, where H is an orientation reversing diffeomorphism. Then we have the following. If we take the type A structure of one of them, it doesn't matter which, and we take the box tensor product with the type D structure of the other, what we'll get is something homotopy equivalent to the closed invariant coming from Haggard-Floer theory of the manifold we get when we glue them together via this map. I didn't tell you about the closed invariant because I don't need it today, because in particular, the point here is that this theory extends over three manifolds with two boundary components. And so this theory, will claim, is well suited for dealing with satellites in the following way. We can take, for example, we can take the type A structure of our companion knot, so of some knot K and S3. So in particular, since this is a theory of three manifolds with boundary, we're actually thinking of the knot complement here. And we'll take the box tensor product with, now we have a bimodule because we have a three manifold with two boundary components. And this three manifold is take the complement of the pattern in the solid torus. So we have one boundary component coming from the pattern and the other coming from the solid torus. And what we'll get here is something homotopy equivalent to, well, we glue one boundary component to the boundary component of the companion, and we have sort of one remaining. So we get the type D structure of the satellite. And sort of why this is a useful thing to have is sort of from the following. So this is maybe the connection to knot Floer homology. If I have the knot Floer complex of a knot, I can quite easily convert to the type D structure of the knot complement. And this is just due to Lipschitz, Oshvath, Thurston original work. And then from there, I can quite easily swap to thinking about the type A structure, because again, remember, they're sort of equivalent. And there's sort of several easy algorithms to use, and this is maybe the best algorithm. Comes from Hedden and Levine. So I can easily build the type A structure of my companion knot. In this case, as I said, I will understand the knot Floer complex of the figure 8. I can easily produce the type A structure. And then this object is maybe more intimidating to produce, but we're lucky that Adam, Levine in 2014 computed this bimodule, which is in general like a highly non-trivial thing to compute. This bimodule for the major pattern. So we've reduced this question to an entirely algebraic operation. And so we'll claim we're going to take the type A structure of the figure 8 knot, box tensor it with the type G structure of the major pattern, and I will get the type D of the satellite knot as I require. Oh, sorry. Okay. So maybe I'll show you what these computations look like. I won't write them out now for reasons that will be clear. So here, maybe I'll zoom out a little bit. So this module that I've drawn to the left, this is the type A structure of the figure 8. Again, maybe of the complement of the figure 8. And then on the right-hand side, this is that bimodule that Adam computed. And so I've given one of them to you in the form of a module, and the other I've just sort of listed out the differential. And so when you take the box tensor product of both of these, I'm sure you can imagine the result is quite large. So maybe the effect will be lost since the orientation of this talk was switched, but it's this sort of quite large diagram. So this tensor complex that you get is the type D structure of the knot that we want, which is maybe, maybe not so, doesn't seem so helpful because it's sort of a mess, but I sort of claim this is quite easy to simplify. So what we'll do is simplify it by first, we'll note that there are these sort of unlabeled edges that I've drawn as bold edges, and these are coming from places in the tensor product where the type A structure and the type D structure that we're tensoring match up exactly. And so what we can do is perform sort of elementary changes of basis to eliminate these edges and just get several connected components. And maybe when we do that, we get the following connected components. I've been told that this coloring it like this is very overwhelming, but I think maybe it's a little bit helpful to see. Maybe it's not. If it's not helpful, maybe I'll ignore it. But once we isolate these connected components, we finally simplify our type D structure to get the following. So this we claim is the type D structure of the complement of our satellite. And then I've sort of drawn them suggestively geometrically because a priori there's no sort of obvious shape to a module, but I've drawn them like this because if anyone's familiar with knot Floer complexes, this gives us a model of the knot Floer complex in the plane. So I've just reduced all of that work to you for you in maybe hopefully a consumable way. So this is the knot Floer complex, or maybe a model of the knot Floer complex of the knot that we wanted to compute. Great. But recall that this is sort of only half the battle. I still don't maybe have all the concordance information that I want. So now I will appeal to involutive, knot Floer homology. I'll zoom in again. Okay. Okay. So Involutive not Floer homology is a theory. It's due to Hendricks and Menelescu, and it's again another refinement of Hager-Floer. And this time, what we do is take some knot in K and S3, although it's more generally defined, but for us, our knots are all in S3. And we'll associate to it something called an iota K complex, which is our knot Floer complex, equipped with a self map, iota K, that is not, I mean, it's not quite an involution, but it's sort of like an involution, and we'll describe that presently. So, this theory is built using Hager diagrams, and we haven't talked about Hager diagrams at all, but that's okay, because in general, most people don't use the definition to compute this map, and instead use some of its formal properties, and that's what we will do here. So this map satisfies the following properties. Maybe I'll remind us what our ring is. So we're still over this polynomial ring. Right, so this map is skew graded with respect to this ring. It is a skew equivariant map also. It's a chain map, which is perhaps obvious from its construction, but I'll just remind us what the chain, being a chain map, implies. And finally, so like I said, it's actually not an involution on the nose, but instead satisfies the following condition, that iota K squares to something homotopy equivalent to the identity plus a composition of two formal derivatives. And if maybe for any audience experts in the audience, this is a map that was originally studied by Sharkar. This is his base point moving map. We claim that if I hand you the knot Floer complex and you know all of these properties, that can be sufficient to make an argument about what the image of iota K should be. And that's precisely what we'll do. But maybe before we do that, I'll give you an example of what these maps look like. So I'm going to give you a model of the knot Floer complex of the figure 8, since it's quite simple. So this is what it looks like in the IJ plane. So it's just one lone generator and then an acyclic complex like this. And the iota K action will denote in this pink. So away from the line of symmetry in the plane, the involution typically acts as one would expect, and in that it sort of swaps the obvious generators of opposite grading, and then when you square it, actually is an involution exactly. But somehow on the line of symmetry in the plane, some sort of interesting things can happen. Now let's see. In this case, this generator goes to a sum of itself, and this one. This generator just goes to itself, and this generator goes to a sum of itself, and this one. And sort of this interesting action is a product of the fact that the structure of this chain complex is a single generator and an odd number of acyclic complexes. And that's what we have in our case as well. And so we'll claim that there's sort of an interesting action in our in the case of the satellite as well. And what that means for us is an opportunity to obstruct torsion. And we'll explain sort of loosely how that looks. But before I do that, I want to claim, again, maybe make more clear the connection here to concordance, and it's in the following way. So what we claim is that, and this is the recent result of Kang, Park, and Stoffregen, and they're the ones that sort of first suggested this as a proof technique. And this is based on earlier work of Ian Zemke. The following, that if we have two knots that are smoothly concordant, then their iota K complexes must satisfy a certain notion of equivalence, which we'll call almost local equivalence. So it's a local condition. And so in particular, what this means for us is the following. If we can, and this is sort of true in any case, but this is how we'll use it. If we can obstruct a local equivalence map F from the iota K complex of the unknot, which is the identity in the concordance group, to any finite linear combination of the iota K complex of our knot, maybe I'll just write it as C. So if we can obstruct this map for any finite n, then we have obstructed the torsion of the knot. Okay, and that's sort of exactly what we will do. So I will outline what that proof looks like here. Right, so maybe I'll just give you the iota K complex of the unknot is quite simple. It's just a single generator. Maybe we'll label it eta. And the iota K action is just the obvious one. And so we'll note that iota K of eta is just eta. And then sort of for technical reasons, since we're looking at an almost local equivalence, what that actually means is that I'm looking at this map modulo the ideal generated by the variables u and v. And all that means is when I'm computing iota K here, I only care about basis elements that map, that show up in the image of other basis elements. So I just care about where actual basis elements show up under this action. And then for our knot complex, I'll claim that the only interesting parts of it are, so maybe we'll recall the shape. I don't want to do too much scrolling, but that it was there was an L-shaped acyclic complex, and there were maybe several boxes, and we claim that the boxes map to each other in an obvious involutive way, and that the sort of interesting things happen between the single generator and the L-shaped acyclic complex here. And we'll claim that the only interesting action of iota K here is that this generator maps to a sum of itself and this one, and this generator just maps to itself. And I'll write that in words as well. So maybe we'll call this generator A and this one G. And what this diagram is claiming is that iota K of A is the sum of A plus G. Iota K of G just goes to itself. And then we claim further, and this is maybe not shown in the diagram and is in general a highly non-trivial thing to show, but we claim we have showed it, that G does not appear in iota K for any other basis elements. And we claim that if it were to, we could remove it via a change of basis, or we could homotope it away. Okay. And so now recall that we claim we're going to obstruct this map. So maybe first we'll say, for sake of contradiction, let's assume that there exists an almost local equivalence. And so an almost local equivalence is a chain map that induces an isomorphism on localized homology, where we think of localized homology as just the homology of these complexes times U inverse V inverse. That's how we localize it. And so we claim the following, that if such an F were to exist, this would imply, let's say we'll consider the map omega that we define to be the sum of the identity plus our iota k that we've computed. And since F needs to be a chain map, then this would tell us that F composed with omega would need to be homotopy equivalent to omega composed with F. So in particular, there needs to exist a homotopy H such that we have this equivalence. Okay. And we'll look at the left-hand side first and note that we're looking at F of omega of eta. And recall this is just F of 1 plus iota k of eta. I've told you that iota k of eta is itself. So this is just eta plus eta. We're working over the field of two elements, so this is just 0. And so maybe we'll claim here now that the right-hand side does not equal 0, and that will give us our contradiction. And so in order to show that the right-hand side is not 0, we just need to produce some element that shows up on that side and does not cancel. And we'll see it in the following way. So since F is a local equivalence, it must take like a generator of localized homology to generators of localized homology, and note that there's only one cycle that generates homology in the iota k complex of the unknot, and so it must go to some linear combination of this cycle that generates homology on the other side, plus maybe some linear combination of boundaries. And recall that A was just that lone generator, so it's the only cycle in our complex. And then now we'll look at the right-hand side in its entirety, and we have omega of A tensor itself n times plus this sum of boundaries plus the boundary of H on eta plus H of the boundary of eta. We'll note this is 0. So this is eliminated. And now we'll just sort of compute this out a little bit using what we've shown to be true of iota k. So this is equal to 1 plus iota k of A tensor itself n times plus omega lambda plus more boundaries. So this is all just boundaries. And then what we get here is that this becomes A tensor itself n times plus G plus A tensor itself n times. And so finally, we can claim that there exists exactly one copy of the element G tensor A tensor n minus 1 times with A, and that this cannot cancel. So sorry, maybe this is contributed by this, and it cannot cancel with anything here. since we've shown that omega of G is 0 and G doesn't show up anywhere else. So we can't possibly have, maybe we'll just say G is nowhere else. So we can't possibly have that this element shows up again. So we have exactly one copy. Therefore, it does not cancel. Therefore, this side of the equation is non-zero. Therefore, F does not exist. Therefore, this not represents an infinite order class. And C smooth. And so in particular, as we've claimed, these knots are not smoothly concordant despite all that we've required they share. And in particular, not only are they not smoothly concordant, but they're somehow quite far from being smoothly concordant in the sense that one of them is a torsion class and the other is infinite order. And yeah, I think I'll stop there. Thank you.
Does anyone have any questions?
Can you pinpoint what's the property of the complex of the Mazur pattern that you need to make your computation work?
Yeah, so it's actually not a property of the Mazur pattern. In particular, it's a property of the complex that you get out. So I guess maybe the question might be, can you look at like maybe a module and a bimodule and know that you'll get an odd number of acyclic complexes in such a way that you'll be able to use this technique? And I would say that the answer to that is like sometimes, depending how comfortable you are with the pattern. I would claim also that this pattern always produces an odd number of acyclic complexes. So somehow this technique will always work. But
so you expect that this, so I don't understand. So you, can you repeat the last sentence you said?
Oh, so maybe I'll just give an example that if I iterate,
the Mazur pattern always is gonna, this technique is always gonna work when you use the Mazur pattern?
Yes, I think I would claim that. In particular for iterates of this knot in particular, I always get an odd number of acyclic complexes in such a way that I'm always able to use this technique. I would maybe claim, just to be careful, that I may need to use a variation on this technique where maybe I would have to look at an additional involution, but I think that this pattern does always produce an odd number of acyclic complexes. There are cases where if your complex is simple enough, just having an odd number is not sufficient to use this technique, but maybe I'll say that all the ones I've computed, I've been able to use this technique.
That's enough to get a contract.
That's right.
I was perhaps sort of related to what Antonio asked. I was sort of wondering, is there some way you can convert this into an invariant of some description? Because at the minute, it seems just to be a calculation. So
Yeah, that's a great question, right? I think like maybe it would be nice to be able to reinterpret this using immersed curves, which is something several people have been working on. There are a lot of limitations to that. But I think, yeah, generally I'm like sort of thinking about working towards that, right? So nobody wants to do box tensor products but me. So it would be nice if other people could use that part of the technique. But I think in general, this local equivalence is sort of like a hot topic right now, using local equivalence or obstructing it in order to obstruct concordance is sort of interesting. But yeah, I think without a reinterpretation via immersed curves for the bordered component, this is like a little bit untractable for most people. So that would be nice, but